This experiment is testing different properties of proteins. Proteins are polymers of amino acids that are held together by peptide bonds. The primary structure is covalently linked. There are other superstructures built on this backbone that make the protein active the way you can see it in nature. In a secondary structure of a protein, the original chain can fold back on itself into either an alpha helix or a beta pleated sheet. These secondary regions of structure can be part of the molecule. It's quite common for any given protein chain to have many helical regions, a number of pleated regions, and some irregular ones as well, which you'll see shortly. On top of the secondary structures, we have tertiary structures, which occur when amino acid side chains interact with each other, making salt bridges, disulfide linkages, and other relatively weak but important interactions. To be active, many proteins have more than one protein chain that are tied together in quaternary structure. And prosthetic groups such as metals or light-absorbing molecules make them active. Any disruption of the entire protein structure can cause temporary or permanent inactivation of the protein. Changes in pH, addition of metal that interact with disulfide bridges, addition of organic poisons, heat and cold can all cause inactivation of a protein due to disruption of the tertiary structure. One of the proteins that we'll be using in this experiment that can demonstrate these properties is phycocyanin. This is a conjugated globular protein which has several chains of amino acids along with chromophores. Chromophores are light-harvesting organic molecules. It's part of the photosystem II complex found in cyanobacteria, which plays an important part in photosynthesis that green algae can use to convert sunlight to energy. In its native properly folded state, phycocyanin is a beautiful deep blue color. It also has the additional easily observable property of fluorescence. When light that the chromophores can absorb shines on it, part of the absorbed light is given back out as light. In this case, the chromophore molecules absorb wavelengths of visible light, and the fluorescence is red. So you have two obvious properties to observe in order to decide if the protein structure has been altered. We can use color and fluorescence. Inactivated protein, especially when completely unfolded and denatured, will be yellow and not show any visible fluorescence. Phycocyanin is easily isolated at neutral pH. This will be isolated from spirulina in a phosphate buffered solution. I first started out by weighing out the spirulina, about 0.5 grams, and this was distributed into two different centrifuge tubes. Then I tried to put them evenly into the two tubes, and then 7 mils of phosphate buffer was poured into each of the tubes. The pH of the phosphate buffer was 7. It was very important to make sure to mix the tubes up, and it is also important not to crack the tubes on the counter as I did. You may start to see some bluish green liquid spill here and there. There might be droplets, and that's because I cracked the cap of the tube while trying to bang it on the counter. And shaking it vigorously was not getting me anywhere, so I decided to use a spatula to stir it. So the spatula can get all the way into the end of the tips. That makes sure that all of the powder in the tubes is moistened and can be extracted. Next, it's important to centrifuge with balanced tubes. This was centrifuged for 3 minutes. And you probably noticed that the lab is a little bit darker at this point, and that is because it is easier to see the fluorescence when the lab is slightly dark. So the tubes are done centrifuging now, so we can pull them out. I can quickly check to see if there is some fluorescence, and I see a little bit there. That liquid looks red now, and you can see the spirulina powder at the bottom of the tube. Next, the liquid was transferred into an Erlenmeyer flask using a pipette. In order to see if the protein is in its folded state, we shine a light on the sample, and you can see that it's nice and red. The liquid itself is dark blue. When the light is shined on the sample, it turns a nice dark red color. Okay, so I'm getting the tubes ready, and each tube gets 1 ml of the protein, and we have 8 samples. There's a control, a hot sample, a cold sample, sodium chloride, ethanol, lead nitrate, acid, and base. Dilute the first 3 samples with phosphate buffer. You can make the observations there. I'm going to put one tube on ice for a few minutes, and then I'm going to add 2 mL of sodium chloride to the tube. And you could observe if there's any changes here. Fill out your observations in the table. My water bath is hot now, so I'm going to put that tube in there for a couple of minutes. Next, I will add ethanol to the sample. You can make your observations once the tube is stirred up. We can shine the light on that to see if the protein is still folded. So you can make your observations there. This is with 95% ethanol. This next sample is getting lead nitrate. So you can see what's happening into that tube. Alright, was there still activity when light was shined on it? Alright, for the next sample, we're going to add hydrochloric acid first. 1 ml of hydrochloric acid. Alright, you can make your observations about the color of the liquid and any other observations. And here's what it looks like with the light shined on it. And now we're going to add 1 ml of sodium hydroxide to the same sample that we just added hydrochloric acid to. And if there's anything that you notice as the liquid is being dropped in, you can make those observations. And when the light is shined on it, what observations do you see? What kind of tertiary interactions are being disrupted when pH changes? Okay, next we're going to add sodium hydroxide 1 milliliter. You can note your observations here. Is there a color change, a texture change? And here's the sample with the light shined on it. Record your observations. And now we will add 1 ml of HCl to that tube that just had sodium hydroxide added. So you can notice the color changes and the light shine on the sample. What do you observe? So I'm going to check my hot sample. This looks very different. You can record your observations in your table, and we'll shine the light on that so you can see what that looks like. Now we can check on our cold sample in the ice. Notice the solution color and when we shine the light on it. Okay, so the hot sample, if we cool it down, will the activity return? And with the sample when the acid was added, what happened? And was it reversible when we added the sodium hydroxide? And with this tube with sodium hydroxide, when we added the HCl back in, did that return the activity? Was that reversible? So it's been a few minutes. We can check to see if cooling down the hot sample will allow it to return its activity. So is the protein going to refold itself after it's been cooled down? is that still fluorescing red the way it was before? And how about that cold sample? Okay, so just a quick review. This is the control where we did nothing but diluted it with phosphate buffer. This is the hot sample that was heated and then cooled. This sample was cooled on ice and then cooled a little bit to room temperature. This is the sodium chloride. This is what happens with ethanol. This was the lead nitrate, and you can kind of see some chunks down in there. This was the acid followed by base. And this was the base followed by acid. Alright, so good luck filling out your observations. Thank you for watching.